Hi guys, today we are going to continue on with proofs, and yesterday we started with algebraic reasoning and we went through a theorem sheet that had all kinds of theorems and postulates and definitions that we can use to help us out, and we also tried a few on our own. In particular, this is one that was assigned in class. I'd like you guys to pause the video now, double check your work, and make sure that everything was great. Well, now that you've done that, what we are going to be doing is we are going to look at our next set of proofs. Like, what do you do when you're not only in the realm of algebra? But there's actually a theorem that I would love you guys to add, and that is the segment addition theorem. And the segment addition theorem is quite simple. The segment addition theorem just says that you can add segments to get a larger segment. So if I have something like AB plus BC, I could add them together and get AC as my overall segment. Now, what we're going to do is we're going to look at what do you do when you're stuck on a proof. Okay, so a lot of times proofs can be frustrating, and the reason why they can be frustrating is complicated, but it comes down to just a few things. First, proofs can be frustrating because they're incredibly nitpicky. You have to watch every little detail. Second, proofs I've heard can be frustrating because, well, sometimes it's so obvious that it doesn't feel like we need to prove it. And last, proofs can get frustrating because there's not one right way of doing something. And it might take a few different methods to figure out how to actually prove something true, or find out, of course, that it is not true. And this is what I would like you guys to do when you start a proof, to deal with the last one. That last one can be incredibly frustrating because there's nothing quite like getting completely stuck, to have that level of anger. And I don't want you guys to get angry. I want you guys to find solutions. So here are 5 things that you should do when you're stuck. The first is go back and just make sure that you have every single given that you need. The second is make sure that you're comfortable with what you're trying to prove. Like, what does it actually mean? What will it take to prove it? Well, you have to know what you're heading towards. The next one is a common thing in geometry, and this isn't just true of our proofs, it's also just true of any problem you're solving. Make a sketch. A lot of times we think pretty well in pictures. Number 4, just go through your theorem sheet and find every theorem to do with the definitions that you've been given, or with the picture that you've been given. So for instance, if I give you a picture of a circle, go through your theorem sheet and where's everything that mentions the circle? Have you used the definition of a circle? Because you might want to. What does it tell you? What might it help you conclude? And if you're dealing with segments, look at all the ones that talk about segments. There's a lot of them. Which of those overlap with some of the things you've been talking about in your proof? And last but not least, work backwards from the conclusion. So sometimes when they feel really obvious, the thing to do is to start with your conclusion and just say, well, why does that feel so obvious? Well, it's because X. And once you figure out that, you can say, well, how did I know I could do that? And then you can maybe add another step backwards. And so you're going and working all the way backwards through the proof. And we're going to see an example of that in just a little bit. But this is the proof I'd like to work through using those methods. So the first thing that I'm going to do is I'm going to identify my givens. I know that I have the segment xy where y is between x and z, xz, and xy is equal to 4b plus 3, xz is equal to 7b minus 1, and I forgot this, but it's really important, xc is equal to 35. Okay, and what I want to do is I want to solve for b and justify each step. So here are my givens. I know that x, y, and z are in a line with y between. And this is frequently the shorthand for on a line with y between. I also have been given 3 different equations, and that is xy is equal to 4b plus 3, xz is equal to 7b minus 1, and yz is equal to that, and then xz is equal to 35. And those are all given to me. But now I need to solve for b, and maybe right now you're kind of like, well, these are all just a bunch of numbers and letters. That doesn't actually tell me much. So I'm going to draw a picture to help me out as I'm solving this. And a lot of times I actually solve my proof along the side, and I kind of go back in and fill in details. So I know I have x, I have z, y is between. I want to make sure I don't mix it up with midpoint, so I'm just going to put it over here. And I know that this section is 4b plus 1 plus 3. This section right here is 7b minus 1. I know the entirety of the thing is 35. Well, you know, when I see this, I immediately know I can do this equation. I can do 4b plus 3 is equal to 7b minus, or man, I'm doing that wrong. 4b plus 3 plus 7b minus 1 will equal my total length of 35. And I can solve that algebra problem, and I know I can. The question is, how did I get this? Well, ultimately what I'm doing here is I'm saying, well, I know that these two pieces added together make the whole thing. So I know that just xy plus x or yz will give me xz. So that is segment addition, and I know I can just add segments. I'm allowed to just add segments according to the segment addition theorem or according to the definition of between. So right now what I have is I have a bridge to solving for b. So I can start to fill in my table since I know where I'm going to be going with my solving. And that means that I'm going to fill in right now my more general terms. xy plus yz is equal to xz. And you may call this two things. The segment addition theorem is one possibility, or you can just call it between, definition of between. Now, I know that what I did was I took 4b plus 3 and I added to it 7b minus 1, and I ended up with 35. And that's because I took each of these equals and I substituted them in. And so that means what I'm using is the substitution property of equality. And now I solve, and this is, by the way, something that people get confused sometimes with. If you are adding on the same side, we're just going to call that simplification. Technically, it's something else, but we're going to call it simplification if you stay within one side of an equation. And that is going to be 11b, 7b plus 4b, plus 2 is equal to 35. I've just simplified the problem a little. Now I'm going to subtract 2 from both sides, or add a negative 2, and that is the addition property of equality. Remember that addition and subtraction are considered the same thing because it's just adding the inverse when you subtract. Then I'm going to divide both sides by 11 to get b is equal to 3. And again, just like with multiplication, or I'm sorry, just like with addition and subtraction, multiplication and division are technically the same thing, because with division you're just multiplying the inverse. So we call it the multiplication property of equality. And I wanted to solve for b, and since I have now solved for b and I've supported every step where I haven't missed any little thing that I did in my thought process, it means that I am done. Notice there, I did, of course, identify the givens. I checked what I had to prove. I even made a sketch. I didn't do as much of the searching for related definitions, properties, postulates, and theorems, but I did do a little bit of working backwards, not a ton, but I started with what I felt very comfortable with, and that was making an equation. And then I took a step, just one step backwards to fill in the missing blanks. But let's try these with something with a little bit less algebra. I want to prove the symmetric property of congruent segments. Now, I know that we have a symmetric property, but currently we have the symmetric property of equality. We have nothing to do with congruent segments. And I want to prove that this is true. I want to prove that if AB, the segment, is congruent to the segment CD, then I can conclude the segment CD is congruent to AB. Now this seems like obvious. Of course it would be congruent no matter which side you have it on. However, obvious things in math have turned out to not be provable in the past, and it led to some really interesting things. So we have to make sure that it's actually true based on what we've discovered. And I cannot use the symmetric property of congruent segments to prove this because, well, hey, I'm trying to make a symmetric property of congruent segments. So all I have to start with is the fact that AB is congruent to CD. Now, when I'm looking at this, really symmetric property is what I'm thinking. And I have a symmetric property. It's just has a bit of an issue because the symmetric property that we currently have is only with equality. And what I'm dealing with here is not equality. But the only thing that I need to do then in order to use a symmetric property that would let me flip-flop these is I need to change this to an equal sign. So I'm going to look through here and say, well, okay, if all I need is an equal sign to use this property, well, do I have any that tell me I can switch between congruency and equality? And I actually do. The segment congruence theorem, also the definition of segments or of congruence, allows us to say that two segments are congruent if and only if they're equal in measure. In other words, AB, the segment, is congruent to BC. I could also write then that, according to this theorem, AB, the measure, is equal to BC, the measure. Equality only ever talks about measure. Congruency only ever talks about figures. This lets us switch between the two. Well, that means that I could take this and I could switch this to an equality. AB is equal to CD, right? And that was the segment congruence theorem. And of course, our previous one was just given, so I'm just going to add that. And if these things are equal, well, I could write CD on this side and AB on this side according to the symmetric property of equality, right? As long as I have that equal sign, I'm good. And if that's true, well, I'm almost there. I have it looking almost the same. I just want this to be segments again. So why not switch this back into segments instead of measures? And then, well, then I'm using the segment congruence theorem. And I've also gone from my if to my then, or from my hypothesis to my conclusion, so I know I've completed the proof, which means the symmetric property of congruent segments is true. I used only other ideas that we've previously learned to prove it, and since it's true, I can now just use it to support my point. I no longer have to go through these 4 steps. I can just jump right from this one to this one using the symmetric property of congruent segments. So you can add it to your theorem sheet because you've just proved it's true. Congratulations. That's one more you get to use. And that last proof really used the ideas that we have with searching for related definitions. And our final one is going to kind of look a little bit more at working backwards. Okay, so we know that LM is congruent to PQ. So this segment is congruent to this segment. And we also know that we have a picture that shows us kind of like where everything is. So I'm going to just write picture, and you can assume that the people who are reading your proof have the same picture as you. Now what I want to prove is that LP is congruent to MQ. That can be hard to prove, but it's not necessarily a complicated reasoning that you did to come up with this idea. For instance, if I just ask myself, well, why are those two things equal? Well, it's because I'm just taking 2 small pieces and adding the same piece to it. So basically, I went from this and I just said, well, I know that LP is just a combination of LM plus MP. I've added MP to both sides. And I know that I can add something to both sides. I'm allowed to do that. And I also know that LM is equal to PQ, and I know that because, well, you know, they were segments, and segments that are congruent will also be equal. That's a segment congruence theorem. So what I'm doing is I'm kind of like bridging backwards to get to my givens from my final conclusion. So now that I have gone backwards and I've found the starting point, I've found my givens, I can work forwards through this proof, supporting each and every step. And I'm going to do that right now. And there it is with some minor adjustments.